So, good afternoon everybody. I'm here, I'm not using Panopto to record this video. I was having lots of issues today getting Panopto to work on my computer, and I have been able to find a different means to record the lectures, and you might see that I've been able to put different video sources together. This is a video I took last summer up in Canada, just behind me. It's not really pertinent to this course, but it was just a demonstration that I can put different displays behind me. Where that becomes useful is now where I can say, look at the lecture that we're doing today, so I can have this and I can be a weather person in front of it, and so I can now sit in front of the notes as we're going through them, and I'll be able to talk to you about the lecture that we're having today. So there will be a couple of bits of news about the administration of the course we need to talk about, so I'll be talking about that first, so the introduction and a bit of administration about the course. And then we're going to go through a review of the concepts that we covered in Module 3, which is a review of statically indeterminate truss structures, because we covered a few different methods and it's been a long time since we covered that. We've all been locked in isolation since then, and I imagine it hasn't been at the forefront of all of your thoughts to review that material on your own. So we're going to go through that today. So let's just go through the course, the introduction to today and the administration. So every course at the university has moved to pass-fail. Now this decision is entirely outside of my control. So for those of you that wanted a letter grade for this course, I'm happy to talk to you, and I'll give you an indication of where you would have performed on this course had I been able to grade you fully. Some of you will be very happy with this news, I imagine, as well. Some of you won't be quite so happy, but this was a decision made across the board. Now lots of universities across the world are making this decision for this semester, so it means that you'll all look about the same on your transcripts, and it will be obvious and very apparent why this happened. For other courses, you can probably appreciate it's very difficult to do any form of assessment over the online period. So my laboratory courses, for example, are very difficult to assess now. So that's why this decision has been made in part. Now, it doesn't mean that it's going to be very superbly easy to pass this course all of a sudden. What this means is I've got to find the right balance in how I can make sure that I'm assessing you guys without taxing you too much. But it certainly won't be effortless to pass. You'll need to watch all of these videos, and you'll need to complete the accompanying quizzes. And you will need to make an effort to get the homeworks in, some of which I've already assigned, and to then the homeworks that we're continuing to do as this course goes on. You need to get them in. It does mean that I'm more likely to be able to release solutions to you guys and allow you to have another chance to look at your homework, particularly say with the truss structure. But if you don't hand that homework in with all of the questions attempted by the time the due date comes, then that's marked as a failure on that homework. Okay, I need you to have made a good effort and really be understanding things, how you're getting there, okay? So you can't just hand me in a bunch of rubbish and expect a pass grade. You need to have attempted all of the questions, and you need to be making a good effort at applying the theory as you've been taught. You can probably hear in the background there's some noises in my apartment. We're all locked down together. That's my wife next to me. She's working at the desk next to me. She's a little embarrassed by the green screen I've obviously got left up behind me. But you'll hear interruptions like that occasionally. You might hear my dog coming in for attention. I guess those are the distractions that we all have to deal with in this new wave world. Slack is the messaging protocol that I didn't introduce it. I suggested it for this course. The reason that I implemented it, and I want to implement it, is because I get a tremendous amount of emails from students. I get a lot from faculty as well, and it's just not always the best way of dealing with things. So if I get an email from a student asking me for technical help with a homework, I know that I'm probably going to get another 20 emails on that particular problem if it's a large class. So it makes sense to deal with some of those things in forums where actually those students' questions can be made public, say. So I'm just going to show you the Slack page. Now some of you have been using it, and that's really good to see. So let's just show you. So the Slack page, this is using the Slack app for OS X. So I'm looking at this now, or Mac OS I think is what it's now called, but I can show you here that students have been submitting their homework, and I've been then replying. So Mr. Al-Jaburi and I had a thread here where he put his homework in, put some questions in, and I've gone through and I've actually released to him part of my solution. So this is part of my general solution written in Python for this homework. I'm probably going to give you the whole thing in the end, but this is going through determining the basic shear flows for the homework problem. So I went through there, and then again Mr. Tilker has given some questions as well, and through he was able to spot his mistake after I suggested where I think he made his mistake. I think it was probably around about where I thought it was, but it's useful to have this online such that, say, when someone like Mr. Tilker, I'm pointing the wrong direction, when someone like Mr. Tilker has a question, it will probably pique the interest of those of you that didn't know you were also potentially having a problem with that part. So if you haven't got on already, I think we've got 49 people in this course. On the Slack site. I don't know how many I've got enrolled in the course. I think it's only slightly above 50, so that's a really good showing. I think I've put a slightly more professional profile picture. No, I haven't. I've got the profile picture that I had on there from the beginning, so I'll try and update that occasionally to reflect my current state of mind at viewing the number of emails I get or whatever. So let's go back to back to the notes now. But Slack's being used really well. Please, if you've got a question, try and put it in there. What I also saw is useful is that some students are using it to help each other out and find the videos. So I've just seen Mr. White asked a question here, so in fact I'm going to answer that straight up. So I'm just going to go back to Slack. So this is where it's useful. So shear center calculation. When providing the answer to the shear flow distributions, is it okay to leave Q2 as a function of theta instead of a function of S2? And I can just reply straight to him on here. I'm actually going to start a thread up here. Okay, so the answer's up there, and the answer's there for all of you guys to see. So when that would have previously been Mr. White putting his hand up in class or someone else putting their hand up, now you guys can do this here, and wherever possible I'll try and do some of this via video like this, because it's useful for you all to be able to see responses, and it just shows people what questions are being asked. Okay, so please, if you're not using it already, please sign up to it, because I will find it useful. I find it really useful already, and the rest of you will find it useful as we go on. The shear center assignment is still due in. This hasn't refreshed, there we go. It's a small latency there. The shear center assignment is still due in this Sunday evening. So as I've said before, I gave this assignment out about a month ago. It's a little disheartening to be getting questions about the basics of how to complete it on Slack already. I know we've had a few issues this last semester in terms of where people are located and whatnot, but you should have started this a little while ago, certainly since I gave you a lot of help in the final weeks before spring break. Okay, so there's not going to be a lot of accommodation for tardiness with this piece of homework. I expect you to get this piece of homework in, and I expect you to have made a good effort, and I expect it to be easy to understand as well. So where your question, for example, says to determine the 4 basic shear flow distributions, I expect you to have found QB1, QB2, QB3 and QB4, and then put a box around that somewhere so it's easy for me to see where your correct answer is. I don't want to have to be digging around in the weeds in your answers. Okay, so let's go to statically indeterminate trusses. We're looking at the... let's turn my computer back on. I just accidentally shut my computer down. So we're going to look at statically indeterminate trusses. Now, we started this module last semester, just before the spring break, and we're going to just have a review of what everything involved in here. So we look at truss structures because truss frames are present in lightweight aircraft. They're present in quite a lot of larger aircraft as well. They are a useful lightweight structure that's able to take a tremendous amount of force by comparison to its structural weight. Now, we also use them for this module because they're really useful to help us understand work energy equivalence in place of traditional stiffness and force relationships. So pin jointed trusses are comprising 2 force members. got a member between two pins here, or two nodes. And we've got a member between it. Now what this means, this member can only take force along its principal axis. It can either be in tension or compression. And the sign convention we use, or the sign convention we use in this course, is that tension is positive and compression therefore is negative. You remove my head, compression is negative. Okay. So that's what a pin jointed truss is. Now we've gone through examples of lots of those in class. Now I'm just going to move myself away off this screen. Actually, no, I'm not going to bother. I'm going to move on. So statically indeterminate. What is a statically indeterminate truss? So we have a calculation that we do whenever we're looking at a truss frame. We've got three parameters we remember. We've got M, and this is the number of members. J, which is the number of joints. And R, which is the number of unknown reactions. So we can tell immediately that if we've got more than 3 unknown reactions, so if we've got 4 unknown reactions, we can't solve this structure. So we can't solve it from static equations on its own. So we can now on here, if R is greater than 3, this is then externally statically indeterminate. Okay, and then if we have got R is equal to 3 or less, then we can determine whether such is statically indeterminate or not, because we can then look at the equation M is less than or equal to 2 multiplied by J minus R. Now this is the equation that tells us whether we are statically determinate or not. Okay, so if M is larger than 2J minus R, say if this ends up being M minus 2J minus R is equal to 1, if that was the situation that we had, then we would have degree of indeterminacy is equal to 1. Now this would tell us in this case that if we'd gone through our truss frame and if we looked at a truss problem and we found out in the first place R was equal to 3, and then we found out secondly the degree of indeterminacy was equal to 1, the first step tells us that it's externally determinate. And what that tells us is, this tells us that we could draw a free body diagram and determine what all of the reaction forces are. The second part tells us that there is a redundant internal member. If I spell redundant correctly. So in either of these cases, we've either got a redundant internal member or we've got a redundant reaction. Now in both of those cases, we need to use the force method to determine what either the force in that member or the redundant reaction is, and then we continue with the problem just as we would have done from 200 or 202. So we use the force method to determine with statically indeterminate structures, and this helps us determine either the Fn, which we'll say is our redundant reaction, or Fi, which is our internal force. The redundant internal force. So we spent a lot of time looking at these two things separately now, because the solution procedure, even though ultimately we're solving the same problem when we're looking at an internal or an externally statically indeterminate structure, we'll look at these two things separately. Now it's easier to look at externally indeterminate structures first, so we'll go through that one. and we'll describe what we're doing with the force method. So we're not yet looking at work energy, we're not yet looking at virtual work or unit work method. What we're just looking at is how the force method works. And I want you guys to understand the problem that we're trying to solve, and hopefully it will become apparent quite why using the work energy method, using the virtual work method, help us solve this problem. So let's pick a problem, one that we've gone through before. So let's just find this. It's one that we went through in class. So say we have this truss structure here. Now we can see, let's zoom in a little bit. Okay, so, and I'm going to make this slightly smaller over here so I'm not going over my text. Okay, so before we follow the steps that it says to take up there, we're looking at this problem. We can do our calculation. We can say, okay, I've got two built-in supports. I've got one down here, and I've got one here. Sorry, two built-in supports. I've got one down here, and I've got one over here, both of which have two reactions. So I can say over here, I've got RAX and RAY. I've got RCX and RCY. So that tells me I've got 4 unknown reactions already. R is equal to 4, therefore we are externally, statically indeterminate. Now we can also go through and check the degree of indeterminacy of this structure. If the degree of indeterminacy of this structure is 1, that's good, because we know that we have a single redundant reaction. So it tells us that we don't need to get rid of any internal members as well. If we go through and we find that it's got a degree of indeterminacy of greater than 1, then that would tell us that in addition to getting rid of one of these, we'd also have to get rid of an internal support. Okay, so that's Mr. White has just thanked me. That was a nice noise in my ear, and that tells me that Mr. White has just thanked me. He said not just thank you, he said awesome, thanks. So it's good to know. I'm not making fun of you, Henry. I'm just it's very weird speaking into a camera and seeing student responses as I'm going on. Anyway, back to this problem. So we can work out what else we've got here in terms of members. We've got 1, 2, 3, 4, 5 members. So M is equal to 5. And then if we were to look at the number of joints, well, we've got 1, 2, 3, 4 joints. Okay, so J is equal to 4. So our equation, let's do it, M has got to be less than or equal to 2J minus R. So that is 5 is less than or equal to 8 minus 4. Now let's go down to here. 5 is less than or equal to 4. Now we can see here that equation is not correct by 1. So our degree of indeterminacy is 1 for this structure. And this tells us that actually, because it's an externally statically indeterminate structure, that's good, because it means that we've only got that external support to get rid of or to look at. So let's remove some of this fluff from around this diagram. I don't need all of this here, because we are just trying to look at the reactions at the moment. So we've got these 4 reactions on here. Now let's have a think about what the reactions are doing in a structure. So if we've got some applied forces, we've got P2 and P1 applied to the structure. What those reactions are doing is they're maintaining static equilibrium. So they are ensuring that this structure doesn't move when those forces are applied. So they've got to maintain equilibrium in the x direction, equilibrium in the y direction, and moment equilibrium as well. Okay, so 3 is the minimum we can have to maintain all of those. And we can see that, well, 3 for this structure is the minimum we can have to maintain all of those. And we can see that for this structure, if we've got 4, we can't determine the number of them. Sorry, we can't determine what each of those reactions are based upon the static equilibrium equations. So it means that one of them is redundant. And if we get rid of it, we could still have a structure that was maintaining equilibrium without it. So just for the sake of this question, and because I've drawn all the diagrams already, we'll get rid of RCX. So we will set this one equal to 0 in the first place. Now this is effectively what I'm being asked here. So I'm saying pick a redundant support Fn at a given node I. So the ith note in this, I was equal to C, and then I've chosen Fx. So what I'm getting rid of is Fcx in this case. I'm setting that to be my redundant reaction. So then we're now going to see how much the structure moves if I set that equal to 0. And this is going to give me the quantity big delta I. So let's introduce the next diagram. Okay, so if I set that reaction equal to 0, what I have effectively done then is I have taken this structure and I've taken what was a built-in support and I've turned it into a roller. I've got to figure out how to get a decent black background on these slides, or get my latex slides to match the background of this other program, because that's annoying how there's that line there. I'll try and get that fixed. So we've turned our built-in support into a roller now, and this means that if we apply these two forces here, we're pulling down, pulling across here, the structure's probably going to move in this direction. So we're seeing how much the structure moves with that support reaction set to 0. There's an important distinction to make here. I didn't mean to highlight, I meant that to be a pen. See how much the structure moves in direction of Fin. Okay, so we're then seeing how much that structure moves in the direction that that reaction was. So let's, I'm not telling you how to do that yet. We're going to go through that in the coming lectures. I'm just telling you the distinction in the force method. So let's put our next one in. So if we then move our structure, or we load our structure, we can see that it's moved a certain amount. So I've got the original structure on in the light grey, and I've got the new structure in the white. I think my wife's getting phone calls in the background and doing her very best to not answer them. Bless her. So we've loaded the structure. Now we remember that our reaction that I put over here, this was Fcx was equal to 0. So the distance we're trying to look at now is the distance this would move parallel to Fcx. So this distance in here is delta I in this case. Okay. I could call it delta Ix if I wanted to. I'm only ever looking in one direction here. So that's the displacement that I'm looking for. So I'm not telling you how to solve that yet. We can solve it using either the geometric method, or we can solve it using work energy equivalence, or we can solve it using, ultimately we're going to have to use the principle of virtual work. Well, actually for this structure we don't need to use virtual work, but I'm just trying to give you an overview of what the force method does. So we're seeing how much the structure moves, so we've got this displacement here, and that helps us. So let's put our structure back. Okay, so this tells us what the structure would do without this redundant support force being there. So if that redundant support force wasn't there, the structure would displace to the right by this certain amount, which we've called delta I here. Okay, so that amount is how much the structure would move were that redundant support not there. So we can think about what that support is doing. That support is maintaining static equilibrium of that node. So Fcx, which you've got here, I'm drawing it going from left to right here, but it's probably going from right to left. It's probably a force pushing the structure back in the other direction, because we would ultimately end up showing that the structure, node C, moves from right to left on screen. So the force needs to be going in the other direction. But that would just give me a minus number in this case. So without that redundant support, the structure moves in that direction. So that tells us that the force that must exist at FCX is just enough to maintain static equilibrium. Just enough such that when that reaction's there, there's zero movement of that node in the horizontal direction. So we don't know what that, let's move down. We don't know what that force actually is yet. So I can just move this down a little bit. Okay, so we don't know what that force actually is. So we just set it to an arbitrary value. I've called this Fn1 in this case. And we can just set this equal to 1 Newton in this case. And we want to see how much the structure would move back in the other direction. Okay, and it's important how much the structure moves when we're looking at it with this method in the absence of all other forces. So we don't have those P1 and P2 on our structure anymore. So let's just move me back because I like having some screen space so I can point out things. And let's move one of our images on here. So we take our structure and we can see here that I've gotten rid of my P1 and P2. So I've no longer got P1 and P2, which were applied at these nodes here, and I'm just applying a single force here. So what we would need to do now in this case is work out what our reactions are. Work out what those reactions are, then work out what all of the internal forces are. So we'll call this F1 prime, F2 prime, F3 prime, if this was our numbering system in this case. And then we'd work out effectively from all of those, whatever method we end up using, you could, for this structure here, just work out what the displacement of these two members are. So we call this F4 prime and F5 prime. If we had those, we could look at the contraction of those two lengths and then determine what the movement of node C is. But we're not really trying to solve this problem, we're just trying to describe the method. Let me bring my last image of this one in. We then see how much the structure would move back in the other direction in the absence of those other forces. So then we've got this new displacement in here. I call this delta I, okay? So this is now the displacement of the structure would move back with a reaction of 1. In this case, we've got our little delta in here, and now this should be a lot smaller for any sensible loading than the big delta, okay? So that makes sense, big delta's big, little delta's little. So we've got our two numbers now, and once we've got those two values for a linearly elastic structure, then we know that actually that condition to give us zero displacement is when our reaction support, Fn, the bit that we're trying to find, is equal to the big displacement divided by the little displacement. Okay, so that's going to help us determine what the actual unknown reaction is for our problem. Once we've got the unknown reaction, we then just apply it as a known loading. So let's go back to our structure here. So we would then start again at this problem. We've then solved for this Fn. We've solved it, which is good. And we would then end up having this force. Now it would obviously be a force going from right to left for this problem. So I then have on here, this would be Fcx. And this would just be a number, an input into this problem. So I then got P2, Fcx, and up at the top I've got P1. I've got 3 inputs, so this I would put a tick next to it because it's known. I would then still have my 3 other reactions which I could solve for, and I could solve for these from the basic static equilibrium equations. So from this problem now, okay, so from this problem, so 1 second guys, sorry, love, what was that? Thank you. Okay. So with those things all known, we could then solve for the internal forces in this structure. So we started out with a structure that had one too many external reaction forces, and we then used the force method, or we spoke about using the force method to solve for the unknown reaction. So in the accompanying notes, which are available online, they're all available on the Blackboard site. Let's just have a look at those. Just check those are actually available. Here we go. So example 3.2 in the notes. I spent a long time writing these guys. They're pretty useful, I think. So example 3.2 is, here we go, an externally indeterminate truss. Where do I have an image of it? Okay, let's try and find it. Here we go. So for this problem here, we can see that we've got two built-ins. So we've got 4 reaction forces, and we can then go through and solve for the total internal forces of this structure. I then end up using a geometric method with this problem. You guys know that I don't think that's the best method to solve these structures by, but just showing you what the force method is and how actually the force method is completely independent of everything that we've learned in terms of using work energy, virtual work, and so on. So please make sure you can go through this problem, make sure that you can understand it in full. Once we'd finished looking at the sort of simple examples with this structure, we then said we've got, well, what if we have a more complicated example now? What if we got something like this? Ultimately, this hasn't got really a tremendous amount more in it. Let's have a look. So it's actually the same sort of problem as the simple one that we went through. It's got the same degree of indeterminacy. We've just got a structure that is geometrically a lot more complicated. So the same procedure we would follow to solve for this, we went through it in class, and I fully go through it in the notes, how we'd solve this problem using the force method and using work energy equivalence. So what is this work energy equivalence? We spoke about it quite a bit already in class. Again, just to recap and to go back through all of this. To solve for the more complicated examples using the geometric method, where we try and unpin and then reconnect all these joints together, it would be time consuming, and I'd make mistakes doing it. I expect most of you guys would make mistakes doing it as well. So we utilize this concept of work energy equivalence. Now, it's a really powerful means to think about structures. When we're thinking in terms of forces and displacements, this can be tremendously complicated because forces and displacements themselves are both vector quantities. They've got a magnitude and a direction, so we have to be careful about the way we add them together. Work and energy, on the other hand, they're just joules, okay? They are scalar sums. So we can think about, if I want to bend something, I'm doing work to the structure and I'm storing internal energy. When I was looking around on my desk for something to pick up and bend there, I managed to find this this phone holster. This is actually bright green in reality, so I think just shows up as being black on here. That's kind of cool. Okay, I'm entertained by simple things, but we use this work energy equivalence to determine the relationship between the work that we put into a structure and how that's stored internally in the structure. We can just remember that energy itself in joules, it is just the ability to do work, so it's stored work. The fundamental thing for this problem is that the internal energy or work must be equal to the external work or energy. I've split those two, I've changed the order of work energy there, and I've done it on purpose because we tend to think about internal energy, i.e. spring energy. We think about that, we think about potential energy. And we tend to think about external work because we've done a force and a displacement, and that's the definition of work. But these two things are always equivalent. Energy is just the ability to do work, okay, or stored work in this case. So that's our governing equation. The sum of the internal energy has got to be equal to the sum of the external energy. We've then got the definitions of these. So we went through this in class. Internal energy stored within each member is equal to half the internal force in that member multiplied by however much that member extends by. So let's just line these up. Started to write that wrong. I'm doing some trouble when I do this from memory here. F-I-L on E-A. Okay, so if we're looking for the extension of member I, we then take the force that's present in it, multiply it by the length of that member, and divide it by both the Young's modulus and the cross-sectional area of that member. If we're looking at the external energy, then it's very similar. We look at the displacement, how much that node moves by in the direction of the force that's being applied. Now the important thing to note here is these two have to be collinear. So if we're looking at applying a force in the x direction, we're then looking at the direction the node moves in the x direction. These two will always be collinear. And that's because if we have a two force member like this, if I've got tension, that has to exist along the principal axis of my two force member, and so does the extension. If I've got contraction, again that force has to exist along the principal axis of my two force member, as does the compressive force that's present within that member. If I've got a node here, now if I'm applying a force in this direction on my node, I've got to be careful that the displacement I'm looking at is aligned with my force that I'm applying. So we're just careful when we look at these two. Why is there a factor of a half in those? This is where I'm asking a question that I probably should be answering, but we've got to remember that we're looking at the energy stored is the area under the stress strain graph. So there's a big section of this in the notes. Let's just go, and I'm again just directing you to more reading here, but let's just go through. Okay, so back into the notes here. So we're thinking about internal energy here. Here we go, virtual work I talk about. I don't want to talk about virtual work, I want to look at, here we go, okay? So we can look here. So if we look at these sections here, go read through and we can understand what these internal forces are and where actually this energy is stored and why there's a factor of a half in this case. So we're looking here, I talk about applying load sequentially over time, and then this shows effectively how we're looking at the area under the load displacement graph, okay, or the stress strain graph if you want. Let's go back to my blackboard. Again, there's another example. Go through section 3.3.2.2. You can tell how wonderfully organised my notes are there. 3.3.2.2 is, let me find it. So, okay, 3.3.2.2, we've got a simple structure here. We're able to, for a structure just like this, we've got a single applied force, which means we've got one force to look at in terms of the external work done, and then we've got three members to look at the internal energy, and we can equate those two directly because there's only one unknown in this case, which is the external work, which is for this one is going to be this delta B here. So make sure you can follow that example through, and this is just going through and understanding what the work energy method is. Now, when we go to look at this structure, again, we can't solve it yet using just our knowledge of work energy, so we have to, we invent this virtual work. Virtual work, I've said in class before, I think it's such a powerful concept of mathematics, or of solid mechanics rather. It's one of the most powerful tools available to us. It's such a startling observation that someone once made, and the key thing is that this force doesn't have to actually cause the displacement to be doing any work. So this means that we can take a structure and we can apply some whatever forces we want, and as long as they are small and we put them there prior to any other loadings taking place, they can just be carried through with any real deformations. So let's draw a really complicated truss structure. Horribly not organized truss structure. Say I've got a very complex structure here. Pretend that it looked nice when I drew it. And say, for example, I wanted to know the displacement of this node here. That's what I want to know. And I've got a bunch of loadings on here. Say it's being pulled up, P1, P2, P3, and P4, P5, P6, and P7. If I want to know what's going on at this node in the center, all I need to do is I apply a virtual force, which I'll call P8. Let's zoom in a bit so I can write that on there properly. I can apply a virtual force there. So I've got a bunch of real forces and I've got some virtual forces now. So we've got a couple of systems in place here. We've got real forces. Now what do these create? These create real reactions and then real internal forces and real extensions. So let's give these the symbols. So this would then give us my real reaction vector, which could be, for this built-in structure, that would actually be 4. I'd have 4 reactions. I'd then get my real internal forces, lowercase f would be a vector, and then I get my real extensions. This would be delta L as a vector in this case. I've then got a second system. I've got my virtual system. These create virtual reactions which we'll say is our vector with a star. We've then got virtual internal forces, and we've then got virtual extensions as well, but we don't actually ever use those. This is as far as we need to go with the calculation here. So let's just quickly summarize how we would actually calculate these. Now when we're looking at the real system, we say all of the F star, sorry, not F star, we say, for this case, P star, which will be our applied loading, is equal to 0 when we're looking at determining these things up here, when we want to work out the reactions, the real internal forces, and the real extensions. We set P equal to 0. When we're down at this next part and we're looking for the virtual system, we set all of those real forces equal to 0. So let's do this here. P1 to P7 for this example I've just made is then equal to 0. And we look at that applied virtual loading. We then take that applied virtual loading and we work out what the virtual reactions would be, and then what the virtual internal forces would be in each of those members. We then are left with the principle that we're trying to equate for this is if the internal work is equal to the external work of any structure, it follows that for us, the internal virtual work is equal to the external virtual work. So we haven't defined what these two things are yet, or in this review session, so we'll just define them now. The internal virtual work, there's no factor of a half in these two, and if you want to go through the notes you can see why there isn't, but the internal virtual work is equal to the internal virtual forces in each member, so So we'll just say this is the sum. Now the sum of all of those forces multiplied by the real extensions. This has to be equal to all of those applied virtual external loadings multiplied by the displacements, the real displacements in each of those nodes. So let's put an n down here as well. So let's just say that's virtual, real, virtual, real. Okay, so we never calculate the virtual extension. There shouldn't be a blue delta L or a delta L with a star above it, because what we're using here, we use the real forces to work out how much each of these internal members extends or contracts with the real loading. We then work out what the internal forces would be in each of those members if we just had that external virtual force and nothing else, and that gives us these two. We multiply them together, we add them up, and that gives us the virtual internal work. We then know what our virtual external force is. It's just 1, because we're smart, lazy engineers, and we apply a virtual force of 1. And then this is the bit that we're normally trying to solve for, which is the displacement of that node in the direction of the applied virtual force. So that's what we went through. I wrote it out. I'm just going to go through it again. We've got those virtual external forces denoted by an asterisk. I've drawn them in red. I've confusingly, I drew them in blue in my diagram below and then red here. I think you guys are capable of understanding concepts and switching colours. We've got virtual external forces which cause those virtual internal forces in each member. And then we've got the whole real system which cause the extension or contraction. And those are the bits that we're looking for. Let's make me really small. I can remember how to use the piece of software. There we go. Okay, so we've got those real extensions. Now, if we can think about how this system works and what we're looking for, we're applying virtual forces to work out what goes on with the real structure. So somehow the information about those real forces has to get into this numerical construct we've made. And the way that that information gets in is from these real extensions. So these real extensions tell us that when we stress the structure with those real forces, for this example I just made up, P1 through 7, that causes each member to grow or contract by this certain amount here. The virtual external force that we've applied just tells us how each force within the structure relates to a displacement at that node. And so that's how this method helps us, because we then work out this construct called virtual internal work, and it's the product of the virtual forces and the real extensions. And then we do the same thing with the displacement of the structure and the virtual force that we apply. And this is why you can see we normally apply a virtual force of 1. So none of this should have been new to you guys, but hopefully it's been a good refresher and a good way to remember the things that we've covered already in class. So we went through this in class before. We went through this sort of quickly in class, but it's written in the notes completely. Let's just go through and I'll just show you where it is in the notes, this problem. Okay, so we've got this problem in the notes completely. I've gone through and I've removed the force at node D, and I've solved for the internal forces. Now, do I go through it? Do I do any more? I think it's maybe in the appendix here. Yeah, okay. So we've got all of the internal forces solved for this structure. Now, what I'd like you to do, and what I'm going to provide a video solution for, but again, you need to do this stuff on your own, is take the structure, don't get rid of node D. Say, make FBX equal to 0. And then solve for the structure again, and you should get all of the same answers here. And this will just show that you can understand the problem and make sure that you can solve problems in slightly different means. Okay, so I want you to go through this and solve for all of the external forces. So let me Make myself big. Okay, so hopefully that's given a good review of all of the stuff that we covered in the couple of weeks leading up to spring break. Don't forget, guys, you've got the homework due in this Sunday. Please use Slack, okay? If you're having problems on this homework, go to the Slack space and put stuff up there. I've got one of these for both of my courses, so those of you who are fortunate enough to be in both, you're able to see all of my courses on here. So put a problem in here, student to instructor, put something in here, okay? Put a question in if you're not certain. Look at what other people have put in so far. Look at my responses, because, for example, in my response to Mr. Al-Jaburi, I've given you quite a bit of my solution here, so you guys can go through and try and understand what this, what I'm doing in here. What is this code? This is written in Python, but it's something you guys can use. In my 319 class, I've got a slightly more professional photo. I had an even worse one. I've just changed it over. They're mechanical engineers, so they're turning it into more of a discussion board for some reason. But I'm happy for this stuff to go on, okay? Because a big thing that you guys are going to miss out on whilst we're all on lockdown are those interactions and just sharing of stupid jokes. So please use it for whatever you want to. I've got some. I can't read that in front of you guys, because what you can do on here is you can send me a direct message as well. So if this person sent me a message, I won't read that in front of the class. If you want to do that and send me a direct message, I'm happy to look at that and I'll respond to you privately. Just what I'm trying to do is reduce the amount of times I have to answer the same question the same means. So if it's the sort of thing that you would put your hand up for in class or come along to me in a group, then put it on here, okay? We're going to I'm also going to be hosting some form of office hours this week. I need to figure out the means to do that. You can probably see I'm playing around with different forms of technology to try and interface with you guys in a means that's can be slightly fun and interactive. I played around with different backgrounds on here quite a bit this afternoon as well, just while I was waiting for the builders to subside. So I'm sure you'll expect me to be posting videos from a variety of hilarious backgrounds that I managed to find. If there are any questions, you know what to do. Drop it on Slack. If there's any feedback on this, let me know. I will always put a link on both Slack and Blackboard for this stuff, and I will start putting up Blackboard quizzes. Now, you need to have done all those Blackboard quizzes. You need to get good marks in them in order to pass this course, so please get them done. And again, any questions, drop me a message on Slack, please.